Well, here we are in Unit 2, Introduction to Parent Functions and Transformations. In this video, we're going to talk about a parent function. We're going to graph the basic parent graphs, introduce the transformations in graph form, or at least talk about the different types of transformations, and then we'll look a little bit at transformations in equation form. There are quite a few functions that we want to talk about in terms of a parent function. A parent function is a function in its most basic form. For instance, here we have the identity function. The identity function is the function y equals x. So if we were to plot a few points on here, we would say if x is -1, then y is -1. If x is 0, y is 0. If x is 1, y is 1. And then you would graph these. You would see that it goes straight, I missed that, straight through the origin. It has a slope of 1 and it goes through the 0, 0. So it's the line y equals x. The linear function that we've been graphing is y equals mx plus b. So if, for instance, we had y equals 2x plus 1, we would go to 1, and then it would have a slope of 2, and we would draw a linear function in like this. So the difference between a linear and an identity function is the identity function is the slope is always 1, and it goes through the origin. But a linear function could it be an identity function? It could also be what we call down here a constant function. A constant function is just going to be a horizontal line. And so that would look like y equals 1 or y equals -3. So here I have y equals 3. That would be a purely horizontal line, y equals 3. All right, now there are other types of lines, and a vertical line, of course, is also a line, but this is not a function. A vertical line is not a function. The absolute value function looks like this. Y equals the absolute value of x. All right, so if we graphed a few points, or plotted a few points here, and I'm picking points that are right around the origin. Okay, so say for instance I do -1. Well, if x is -1, y is 1. If x is 0, y is 0. If x is 1, it's also 1. So I have the origin. I go over 1, up 1, over 1, up 1. And this is the V graph. All right, so this is the parent function for the absolute value. And all you have to do to graph those is just plot a few points, and then you can see that they have distinctive, this one has a distinctive shape. Okay? A quadratic function is y equals x squared. Now, to graph that, we would also plot a few points. -2, -1, 0, 1, and 2. If I put in -2, -2 squared is 4. If I put -1 and square it, that's 1. 0 is 0. 1 is 1. 2 is 4. Notice that none of the y values are going to be negative, right? Because when you square a negative, you're going to get a positive. So if I have -2, so I have 0, 0, over 1, up 1, over 1, up 1, over 2, up 4, over 2, up 4. So we have a symmetry. All right, I'm going to try this one more time. This thing is really small. Okay, don't freak out, but I made it a little bit bigger because, well, honestly, I just couldn't deal with it that small. So we have 0, 0, over 1, up 1, over 1, up 1, over 2, up 4, over 2, up 4. And you see it has this lovely little parabola shape, right, with a domain of all reals and a range of 0 to infinity, including 0. So you'll see once again it's a curvy version It's not like absolute value where it's a V, it's actually a curve, right? It's symmetric about the y-axis, and so it has y-axis symmetry, and we can find the domain and range. The cubic function is y equals x to the third power, and if I plot a few of these points, if I have negative 2 to the third power is negative 8. If I have negative 1 to the third power is negative 1. If I have 0, 0, 1, 1, 2, and then 8. So at negative 2, I go down 8. 2, 3, 4, 5, 6, 7, 8. So here. And then over 1, down 1, 0, over 1, up 1, 2, 1, 2, 3, 4, 5, 6, 7. I can't count. 2, 3, 4, 5, 6, 7, 8. And so it has this very distinctive S shape to it. And that's a cubic. And its domain and range are both all reals. So that's what the basic graphs look like. What we're going to do now is we're going to use transformations to take these basic graphs and move them and stretch them and shrink them and reflect them so that they start looking like these kind of graphs, but they end up looking slightly different. So for instance, you can see some graphs right here that either have been translated or maybe not even translated. Maybe they're just moved right or left. All right, so this one right here, this right here is the absolute value graph. And it's moved to the 1, 2, 3, to the left 3 units. Do you see that? Normally it starts out at 0, 0. The V part of it starts at 0, 0. It still goes over 1, up 1, over 1, up 1, so it's not been stretched or shrunk in any way. This one is also a quadratic. We know that this parent function, but it's usually, the parent function starts here at 0, 0, over 1, up 1, right? But it's been moved to the right 2 units. Okay, this is the constant function. It has been moved up 2 from the x-axis up 2, and this is the equation y equals 2, right? This is the identity function. This is a much better graph than the one I did. This is the y equals x. This was y equals 2. This is y equals x. This one up here is y equals x minus 2 squared. It's to the right 2. And this is the absolute value of x plus 3, which is to the left, 3 units. So there are 3 basic types of transformations. Translations are moves to the right or the left. And if you're using function notation, it looks like this, x plus or minus h. They can also go up or down. In function notation, it looks like this, f of x plus or minus k. So notice that this is inside the parentheses and this one is outside the parentheses. Reflections look like this. So if a parabola looks like this, a reflection would make it go upside down. So it's usually a reflection across or over the x-axis. Occasionally you can have one that is a reflection over the y-axis. Okay, but this one is just flips it upside down, so this is a reflection across the x. And if you're doing function notation, that would be negative the function, negative f of x. A stretch or shrink, so if you have a parabola that looks like this, a stretch would look like this, skinny. And so that would be something that you would multiply times the outside of the function. That would be a stretch. Now a shrink would look more like this. And what you're talking about, a stretch is stretched away from the x-axis. And this is towards. the x-axis. So in class, we're going to do a discovery activity for both the parent function and for the transformations, because when you get really good at this, you'll be able to graph something based on an equation without having to plot any points at all. You'll be able to know which direction to move it up or down, whether it's stretched, whether it's reflected, and you'll be able to apply all these transformations to a graph without having to plot points or put it in your calculator. You'll be able to graph it by hand. That is our goal. So I hope you took good notes, and I will see you in class.